Let's talk about the last sort of section on these bits, which is the additive and subtractive manufacturing. So first of all, additive. So additive, as I said, really additive support was introduced back in Creo 3 to connect directly up to some supported 3D printers. Okay, uh, probably the big thing was in Creo 4, they just introduced the lattice feature. So the idea is the ability to build your 3D or your printed lattice 2.5D or 3D inside your CAD model, with really the idea that you want to validate that inside CAD. So if you're going to 3D print production parts, you're going to put a lattice in that side. Inside those parts, you want to make sure that they meet the structural requirements. So the lattice feature was introduced there. We could build that. There's been enhancements to that along the various versions of Creo. We introduced stochastic lattices, formula-driven lattices, and the like as well through later Creo versions. So inside Creo 8, with the lattice, one of the big things is around the ability to define lattice variability based on simulation results. So previously we had the ability to define variability based on just geometric references, sort of manually typing that in. But now we're looking at this as being sort of design driven or requirements driven. So the idea is that we can take our part, run a simulation on that part. That could be in CSL or Creo Simulate. We can take those results. If it's CSL, we export them out, and then we can use those results to then define the density of our lattice as we build that. Okay, so here we can see that we've got our lattice feature. There's some variability. It's a bit hard to see in the screenshot, but we'll see in Imran's demonstration later how that works. And then we can validate to make sure that that meets the requirements. Okay, so you can get different results depending on the types of lattices that you're building. So if you're creating uniformly distributed lattice, our sort of beams, then basically it stays um, the distribution stays the same, but what we're doing is making the beams and the balls thicker in those areas of high stress. If we're using stochastic lattices, so these more sort of organic little beams here, then basically the density of those increases in the areas of high stress. Okay, so we can build those, we can ensure that we're basically meeting our simulation requirements. We can define a few controls over that in terms of volume fraction for our mass percentages, maybe some stress cutoffs for there, get that shape. And then we can even take that, once we've built our lattice, because remember the lattices are parametrically controlled, we can then start to integrate that in with more advanced, other PTC advanced simulation tools like behavioral modeling extension to make sure we're achieving certain design goals. Okay, so other parts to the additive manufacturing extension. So stochastic lattices, these sort of lovely, sort of more organic shapes. We can now create a solid representation of those. So previously you could only create a simplified. Now that was still supported when we went to printing. If we went to into Creo simulation tools, all that was in there. But basically, if you certain file formats didn't support that, so now we can export out full geometry. Okay, so now we can export out STL files or things like that. Probably unlikely. 3MF is really the way to go with printing these days. But also, if you need to take it into other downstream tools, we've got a full representation. Okay. We also have the ability to individually delete individual beams inside the lattice. Okay, so if you've got your weird, wonderful shapes there might be certain areas where you just don't quite like what it's built. So you can go in there, use the remove feature to individually take those out. All right, on the still on the stochastic lattices side of things, there's now support for trabecular shape for these stochastic lattices. So this is an option that's there. If you go into the research on this, it's really around essentially reducing the shape deviation of those cells that the system generates. Okay, so it tries to minimize the standard deviation between the cell sizes to give you some sort of more consistent, even sizing throughout. So this is really these stochastic things are really good for things like medical implants where you want sort of bones to fuse in and stuff like that. So the trabecular shapes come out of some of the research into those sorts of tools, in those areas. On the formula based or the formula driven lattices, so these were the gyroid and diamond and primitive cells that were introduced back in Creo 6, I believe, from memory. So essentially the tool or the algorithm used to build those has been converted over. This is part of the Frustum acquisition that PTC made a couple of years ago. So it's using that new Frustum engine. They've ported that across into Creo. So it's using that new engine for building these. So if you've got any existing models that we're using, the older method of calculation of those, when you open up in Creo, it'll ask you about switching them over. Okay. So another option that's there is the ability to create, when you're using these formula-driven lattices, is to create complementary bodies. So rather than just creating the lattice, you can actually create bodies that represent the empty space that's in there. So why would you do that? Okay, here's an example where you might be building a heat exchanger. Okay, so you've got your two different temperature liquids coming in, whatever they might be. You're building some sort of 3D printed baffle inside that. Then you can actually create the bodies that represent the fluid from each of those two different inlets, to then use that downstream for your simulation, your fluid simulation, whatever that might be, your thermal calculations. Okay, so the ability to basically automatically create those additional bodies as you're creating these complex lattice shapes. All right, another part to the additive manufacturing extension is around the build direction optimization. Okay, so basically there's a bunch of tools in there when we're 3D printing, particularly in metal. Okay, it's very important to do things like minimize the amount of support material that you need, because that will mean more post finishing. Now, if you're printing in plastic, that's a lot easier because generally the printers might have multiple materials. They'll print a different material for support structures, so that can break away and it's a lot easier to clean. But when you're doing metal printing, you basically have to machine that off. Okay, so you really want to minimize the amount of that. So there's a few more options there around optimizing and calculating that build direction. Okay, and also with the print tray assemblies, so you can create an assembly of multiple items to send that off to your printer. There's now the ability to basically multiple assemble parts. Okay, so we can pick, our sort of 3 parts that go into this assembly as a multiple assemble. We just type in the quantities of each, and it puts them in there, and then we can start to use the automatic arrange and things like that to space them out on the tray. All right, so what I'll do is I'll hand back to Imran to have a bit of a look at some of the new stuff in the simulation-driven lattice.
Thanks, Alan. Okay, so I guess the idea here is that we'll have a look at simulation-driven design and focusing on lattice creation. So first, when we jump into live simulation, we can just inspect our simulation tree. We can see that we've got some constraints, which is at the bolt holes, where this object's going to be fixed, and then we have a moment acting about that bearing surface. So these are our loading conditions that we want. So before we run our study, we can choose the simulation quality. So depending on the resources available to us, so your dedicated graphics card and how much video RAM you have, you can refine the mesh that way. And then it's a matter of clicking simulate. We'll give the program just a moment to run, and we can see our results being generated. So here we go. So we can track it. We can go ahead and inspect our model now. So identifying the max and min points. So if I focus in, I can see that in our bolt hole, that's where our maximum stress is going to occur. So we might want to reduce that. We can go ahead and change whether we're looking at the von Mises stress, deformation, and so on. And then likewise, we can choose the max values, the render states, and so forth. We can animate our model, so we can see if the conditions that we've actually inputted for our design study are accurate and produce the result that we are intending. So we can see that, yep, this is operating as we expect. And then now, if we want to go ahead and export our results out for use later on, we simply hit export results. And what we're going to do is specify a number of probe points. And the program is going to go ahead and take into consideration things such as the deformation, the von Mises stress, and write that at those different probe points throughout the model into a results file. So we simply save that away. For the sake of this demonstration, I've gone ahead and created an additional report which takes into account, I guess, more probe points. So it would just scale. It took me about a minute 30 to generate 1,000 points. So as you can see, that was only 50 points and it was fairly quick. So really just dependent on the resources you have available to you. And then now let's go ahead and use those results in our lattice creation. So jumping back to the model tab, we'll hit lattice. And then now what we want to do is define the body that we're creating the lattice for. So I'm selecting that outer surface and we'll choose to create a shell. And I'm just going to define a 2mm thickness. We'll go over to the cell type, which we can see. I'll just scale it down. And then we'll jump over into the cell fill. So we have a bunch of different options. I'll choose to use the star, and then we'll just input some values. Once we're happy with that, we can jump over to the density tab. And this is where we have the ability to input that simulation data and drive our lattice creation. So I'm going to go ahead. We have the option to use simulation data as well as Creo Simulate Live data. So selecting that, I'll go ahead and populate some of these results again. And then once we're happy with our inputs, we can go ahead and preview the geometry. So Creo is going to go ahead and create this complex geometry. So in more recent versions of Creo, this process has become a lot faster. And as you can imagine, for a lattice, it's quite complex in terms of the structure, the overall structure, which you'll see in a moment. So we can track the progress down in the message log here. And once this is finished creating it, we get our finished lattice generation. So when we're happy with that, we can go ahead and OK the creation. Creo will create it and define it as a feature within our model tree. And we'll have a look at that lattice structure and how its density is changed based on our simulation results, like Alan mentioned. So we'll give it a second to process. And there we have it. So I'll take a section cut of the model and let me just reorientate that view. And as you can see, if I hover over the lattice, in areas of higher stress, we've got these thicker lattice structure, and then areas of lower stress, we have these finer beam structures. So at this point in time, we can go ahead and rerun our simulation. I've chosen to use Creo Simulate. So as you would imagine, we're just clicking over. We have our simulate interface. We can define our loads and constraints, which I've previously done. And then we can go ahead and run our analysis. So for the sake of this demonstration, I've gone ahead and run this analysis. It took me approximately 3 minutes to run it for the entire geometry. And I'll pull that information up now. So here we can see the stress and deformation of our structure based on the lattice creation. So we have that edge, the 2mm edge, as well as the lattice structure. And then as you would within Creo, we can go ahead, modify this, update our render scales. So we can localize where exactly this force is happening. And we can go ahead and edit as we normally would within Creo Simulate, changing the units and so forth, hiding and showing additional windows, and changing from stress, rotate, all the other different options that we have available to us. So that's the end of this part of a simulation-driven design. I'll hand it back to Alan to continue on.
Thanks, Imran. All right. So let's move on to just a quick little bit on subtractive manufacturing. Okay. So what's the big new thing in Creo 8 for subtractive is a new module, which is 5-axis high-speed machining. Okay. So this is a new module called High-Speed Milling Plus, which is a basically dedicated 5-axis machining using lots of high-speed machining processes. So this has been built by ModuleWorks. So PDC's partnered up with ModuleWorks for a while now on some of the manufacturing stuff. They're creating the material removal simulation tool. So back in Creo 5, there was a mold machining extension introduced, which was using the ModuleWorks tools for toolpath calculation. So this was a lot of high-speed 3-axis machining. So the new high-speed machining plus is bringing the ModuleWorks in to add in their 5-axis machining capabilities. Okay, so there's 7 new 5-axis toolpaths that have been available. So some stuff, that have been introduced. So some 5-axis roughing, 5-axis rest roughing, some automatic 3+2 machining. Okay, so basically, if you've got a 5-axis machine, doing 3-axis roughing across multiple faces. Okay, so to reduce the amount of tool change and tool or jig setup and changes. Also, new auto deburring toolpath in there as well. So a whole bunch of new options in there. Those of you who are doing the machining, best thing is to reach out to Taju. He can give you the real rundown on all of this as our machining